So we left off yesterday trying to complete this diagram in our notes. Make sure you take that out. All right? And this is where we left off yesterday. I took a picture of it so I knew exactly where we're talking about. I know that we had homework last night. I know that I gave you a key. I also know that I gave you a video to watch. Hopefully you went over that. I also know that you probably have some new questions. Okay? And I'm going to try to answer them with this little extra called spontaneity we've been talking about happening here. So it all does fit together. Okay? I'm giving you the intro. There's a lot going on here. You probably thank the heavens you guys either had some chemistry before you walked in. Can you imagine? Would this look like anything if you didn't spend some time this summer? All right, obviously. Okay? But the basics are the same. So let's continue our discussion here. All right? And as we talked about, let me just turn down the, I think there's some feedback here. Okay, so we clearly are separating what's getting oxidized and what's getting reduced. We should know from the standard reduction tables, which we got from the standard cell experiment, which basically measured how well one chemical can push, oxidize, how well another chemical can pull, take in electrons, or reduce. Those are the basics. And we have those values. And what we do is see how well the one who oxidizes, it's a key, the one who oxidizes, when you do an overall net potential called E0 of cell, okay, on some standard conditions, we can evaluate that. So, what do we know? From the reduction potentials, the one who oxidizes, I flip the sign. Because just by convention, when I say convention, I mean someone came in a big group and said, let's just make him enlist in reduction. We could have made a list in oxidation. It doesn't matter. One or the other gives you the same information. Why? Because if you're really good at oxidizing, you're really what? Terrible at reducing. So on the table, this is negative, .-76. But we know better. If we're going to use the opposite, we just change the sign. Okay? Because we know having a direction, remember spontaneity is a pathway. If you're really good going one way, it means your pathway in the reverse can't be good. All right? So, in any case, this one is as written in our standard reduction potential, and we add them together to get max volts as 1.10. We know that the zinc, in this case, anox, always the case, is the place of the anode. The zinc oxidizes, and you need to understand that anytime you've got a metal that's a zero, it's in the solid phase, and it goes to an aqueous. So a piece of the solid zinc becomes an aqueous ion. It's getting smaller. It's being etched away. And one of the reasons why batteries die is that the anode gives out. All right? Now, who's pulling the charge? The zinc is pushing it, and the copper is decently good at pulling it. This is not a negative. So the copper +2 in solution at the place where there is reduction. Understand this. The action of the redox occurs at the electrodes. Sometimes the electrodes themselves are undergoing a reduction or even oxidation. Not all batteries have the anode breaking down. There are different batteries, but it happens at this electrode. They're normally metals because they have to be able to conduct the charge. So oxidation occurs at the anode, anox, red cat reduction occurs at the cathode. It doesn't mean that copper gets reduced. Copper can't reduce. Metals can't gain electrons. You got that. Copper never becomes copper -1. So this is just a place. It's the copper +2 that gains and pulls along. And as we can see, we figured out what our voltage should be. And we've got 0 because we're missing an important part of this. And what's important is we're missing, of course, the salt bridge. So when I put the salt bridge in, okay, we're going to get a voltage. Because right now, probably a little bit of this happened, and right away, boom, the whole process became spontaneous or non-spontaneous. By having 0 volts, what is it screaming to you in terms of spontaneity? Is there a redox reaction occurring right now? No. Volts are tied to the pathway. Remember, voltage is what? What is a voltage? Yeah, it's the energy to push the charge around. If you don't have the energy to push the charge around, you cannot have flow of charge. Remember, there's amperage, how much charge you push around. That's not what we're talking about. We're talking about the ability to push the charge around or pull it. In this case, it's a combination of push and pull because they're both good at doing it. That's why it's a combined effect. What if, and this is a good question, what if this one was a negative 0.34? Yeah, isn't this good enough to still force the action? And you can see some of its power would have to be diminished. And the overall would still be positive. What would you say about the pathway if this was a negative 0.34? It would be less, right? Less voltage. See, if you're getting that, awesome. Awesome. Okay? There's going to be parts of this stuff you won't get until the end of the year, but I'm going to help today, hopefully. Okay? Now, right now, there's no pathway. Right now, you can consider this to be equilibrium. Okay? Now, we'll talk about what that means in a second, but putting the salt bridge in means now it's spontaneous. I have voltage. Whoa! Far less, it's 0.53, far less than the 1.1 volts I should get. Why is it different? Shouldn't it come out to 1.1? Yes. Okay, what else? Why am I different? It's not so much how much of the anode, because we can't measure a concentration of zinc. Zinc metal is zinc metal, so having less of it really doesn't come into play.
You're running out of copper ions?
Ah, that's a good one. Right, over time the copper ions are disappearing and this is getting lighter. That's a great answer. Okay, this battery is dying. Yesterday it was 0.7, 0.8, now it's dying. This battery is dying. This reaction is dying. We'll get to that. Now what's the salt bridge doing? Okay? Well, in this salt bridge, and I'll just take away the overall reaction here. In this salt bridge, I have two ions, Na plus and Cl negative. Sodium chloride dissolves. Why? Why does NaCl spontaneously dissolve into the ions? It's spontaneous, but what do you think the reason is? Yeah, but why does it do it besides the answering, well, it's spontaneous? What gives the ability of sodium chloride, solid, to become the free ions, which is aqueous? Well, yeah, the water gets in there and breaks it apart. What do you think the attractive force is between things that are positive one and negative one are? Well, they're strong, but are they as strong if they're +2, -2? What law is coming into play here? What law do I keep writing every day? Force is equal to K, Q1, Q2, distance squared. Coulomb's law. Now, is +1 and -1 the lowest whole number of charges you can have? Yes. The answer is yes. Okay? So if you're +1 and -1, these values aren't that big. Okay, now, let's think about a table you guys are going to see. I'm going to put it up here. Okay? You guys are going to see something called table foo-foo. Yep, table foo-foo, wherever you are. Here we go. So table foo-foo. I call it table F. Well, it actually is table F, but I like these pet names. A little creepy, I guess, but hey, we have all our... But there's table F. Table E, I can do my alphabet sometimes. Here we go. Here's table F. Let's get up close and personal. Whoa, my first date space. Okay. What does soluble mean, you think? Something, right, you guys learned it's a homogeneous what? Mixture. And it's a solution. Just like the copper ions is a solution, they're equally dispersed. Now, what does it mean? If I have any salt that has these ions in it, group 1 you should know is the alkali metals, they're always soluble, no exceptions. Why? The charges are what? Too small between them. They don't attract each other very well, right, party people? Salt, or this type of, this is my model of sodium chloride, the smaller one is the what ion? Which one got smaller as it became an ion? Now, the chlorine gained an electron. Sodium lost an electron, right? The protons outnumber electrons, boom. So this is the sodium. But the bottom line is +1, -1. They don't stick together that strongly, so water can come in and pull these apart. Famous boyfriend, famous girlfriend. You notice something that's similar between all compounds that are soluble. They have a low charge. Now think with me right here, party people. Look at the nitrate. It's 4 atoms. 4 atoms spread over what? A -1 is spread over 4 atoms. What do you think the distance is for that polyatomic ion? Compared to an ion, it has to be what? An ion is a particle. This is going to be like a molecule. Sodium is 1 atom. This is 4 atoms. Much bigger. There's 4 atoms. And I got a -1 being stretched over 4 atoms. What's my distance? My distance really got big. And if my denominator gets big and you square it, that's your force. Right. So doesn't that make sense? That anything with 4 atoms or a bunch of atoms and has a small charge, of course it's going to break apart into water, which what soluble means. They make you memorize this in college. You don't. If you've got small charges, water can compete and pull them out. If you've got small charges stretched over a large what? Area, I call it charge density. If you're big with a low charge, you're stretching your charge over a large area. I'm a big person. What if I'm +1 and something is -2? Well, this can't attract me that much no matter how big this charge is. Why? Because it never feels the entire +1. My +1 is stretched over my entire body. I call it charge density, but the same thing is big D equals a low force of attraction. Isn't that logical? You can memorize this if you'd like, but I need you to make sense of it. Isn't it logical? So all of these guys are what? Soluble. Which is important because you need to have what moving up and down? You need free ions. So in the question last night, they said which one is more applicable. The best choice was finding the one where it's +1, -1. Okay? One of the choices last night, I believe, was copper sulfide. Now, you look up sulfur. It's under oxygen. Oxygen has become -2. Sulfur is -2. Copper must be what? Ooh. +2, -2. What do we have? Higher Qs, right? Therefore, copper sulfide is not soluble. It's insoluble, which means it doesn't break apart into free ions, and it can't do anything in the salt bridge. Yes?
Can something be more soluble?
Absolutely.
So acetate.
We can measure things based on every compound has a unique amount of solubility. And how do you measure that? How much stuff can you dissolve before it stops dissolving? It's called the saturated solution. In fact, that was a great question. Let's go to that. There's another table right here. These are called solubility curves. Now, it depends upon how fast the water is moving. This is based all on 100 grams of water. So, at 50 degrees Celsius, this is one we can see. This is ammonium chloride, +1, -1. So at 50 degrees Celsius, 53 grams of ammonium chloride can dissolve in 100 grams of water. That's its saturation point. Anything more than that, it starts to what? Stay as a solid. Now if I increase the temperature, make the water go faster, I increase the solubility. But at the same temperature, look who has worse solubility. KCl. So you're right. Okay? Now, let's get back to where we were, table of foo-foo. Alright? Who makes insoluble compounds? You see anything that comes up that's familiar? The charges are too what? So therefore, they attract too much. Make sense? Now, why is there exceptions? Because I could be negative. This could be what? -3, but if I'm a big +1, like what? All group 1 ions are, or a group of atoms, they still can't track that well. Logical. You're not memorizing. It makes sense. Okay? So, back to reality. Up there goes gravity, and I just rapped, which I don't like to, but hey. And I'm Brassica wrapping in biology too. Remember that? Okay. All right. Okay. So I've got these free ions. Too much fun. Now that I know why I can have free ions and why sodium chloride can dissolve, what does it do? Well, in this side, I'm increasing the amount of what? This zinc plus 2. This beaker is getting positive. Can electrons flow from the anode to the cathode or charge if this becomes positive? The answer would be 9. No! So I need something to move down the salt bridge, and that would be the chloride ions, the counterbalance, and of course there'd be 2 chloride ions that come down for every 1 zinc plus 2. And of course, sodium chloride's everywhere. The Na plus would come down and do what? Replace the positive that's disappearing. And in that way, we keep electrical neutrality, or we maintain a neutral charge in both beakers, or we prevent equilibrium. There's many ways to explain that. Okay? Now there's also some more movement. Can I just add copper ions? Not really. You know what I added in here? I added copper nitrate. Remember this? Is copper nitrate soluble? Anything with a nitrate is soluble. Why? It's -1, and you're stretching that -1 over a big area. So what does this do? This breaks apart into copper plus 2, and I have to have what in here? Nitrates. So this is a polyatomic ion. What do you think it does? It spectates. It doesn't do anything except, hey, isn't this beaker getting positive? So don't you think that this might move this way? Also, to counterbalance? And the answer is yes. So the salt bridge allows ions to flow so that we maintain electrical neutrality, or we make sure that the charges don't change in the beakers, or keep check of the growing positives and lack of positives. Many ways to say that. But without it, there is no pathway. Electrons do not travel. Okay? Now, the questions that people are having are, Mr. Grotsky, what if I change some of the concentrations? I know people are not quite getting this, and that's okay. It's a little extra spin. So let's take away this, and I'll add the overall reaction again. It's zinc 0, that's a reactant. Copper plus 2 is a reactant. Notice we're separating them. We get what? Zinc plus 2 is a product, and make pure copper. Okay. Now, can I change the concentrations of solids? No, you can't. When you say a concentration of a solid, it makes no sense. A concentration means one thing mixed with another. So if you're just a pure substance, like a metal, substance, right, an element, you're not a mixture. When you have a mixture, you want to know how concentrated or how dilute. And we measure that with molarity, big M. And basically big M is molarity, molar is equal to the moles of the stuff you're dissolving over the liter of the solution. So this measures moles of the stuff you're dissolving. So these would be moles of ions or moles of the solute over the total liter of solution. That is a concentration we'll use all year long. So the only thing that has concentration is what? The aqueous solutions. If you're a solution, you're a homogeneous mixture. Now, party people, battery's dying. This voltage that we get is based on what? Standard conditions. This little 0 means it's spontaneous this much under a set of conditions, right? Gasoline in a tank spontaneously will react with oxygen, okay, under a set of conditions. Room temperature? Absolutely. Even if it's not reacting right now, we say there is a pathway present right now. It is not spontaneous at absolute zero. Okay? Or it's not spontaneous when there's no oxygen present, right? That's the reason why we can snuff out a fire. So this is the perfect spontaneity at these set of conditions. What are they? 1 atmosphere of pressure, 1 molar concentrations. Yes? And 25 degrees Celsius or 298 Kelvin. Those are the conditions that little zero means. So this is only when you're at those conditions. And as you just said, Idan, these things are changing. The copper is what? Running out. I don't care if you replace it with what? Sodium. Sodium's not going to pull on the electrons. So you're running out of copper. So the concentration of the copper plus 2, I should say, is going down. It's changing. It's not at these perfect conditions. But there's an underlying theme of why this is dying. That's what I spent all morning writing up in the notes. So what I'm going to teach you now is totally written out. I'm just going to put this on. So why is this dying? Besides the fact that we're running out of copper, what else can we say? Okay? Well, let's go to the website, my class website. I spent all morning writing this up. I'm so excited. Okay.
Mr. Gordon,
Yeah.
can like the salt bridge run out of ions?
The salt bridge can run out of ions. Yes, that could be one reason why. And I'll tell you, usually batteries die for 2 reasons: anode runs out, and or the salt bridge fails. Absolutely. However, even if I run out of Na plus and Cl negative, okay, can't the nitrate move over? And I forgot to mention, who else can move over? Isn't the zinc plus 2 being given off? Couldn't that move over? Couldn't the zinc plus 2? Couldn't the zinc plus 2 be attracted to the loss of positive over here too? So the zinc plus 2 can move. You're building up zinc plus 2. It could move because you're losing your positive over here. So to say the salt bridge runs out of ions probably isn't the best, because you could exchange the extra zinc plus 2 to attract to the negative side. And the negatives just in the nitrates can move over. What fails in a salt bridge is the ability for the ions to move. Loss of water, the physical permeability that allows them to go. And today's lab will have that. Okay? So, let's continue with why the battery is dying. Okay? For those who just walked in, I need you to listen to what I just recorded for this first part. I finished our notes here. So you'll have that to listen tonight. I'm going to continue on with parts of where you probably had maybe some issues with the homework. Maybe you didn't. Okay? I know some people spent a lot of time with me last night. Maybe you got something out of it. I know it's hard work, but I'm trying to ask you to understand. All right? So I'm going to continue on. The question, before we get to lab, is why my battery's dying. Now it's down to 0.53. I think when I started this was 0.77 the other day. My battery's dying. Idan said, I'm running out of copper ions. And he's right. This beaker is not as blue as it was. The blue color is because of the transitional ions. We learned why. So he's right. We're losing my copper plus 2, which is a reactant. That should make sense to you. We're not as spontaneous. My pathway for this process to occur is decreasing. Okay? But that's still not the best answer. Part of your homework was opening up your eyes, okay, to what this really is. All right, so let's take another reaction. All right? Let's look at a reaction with double arrow. Okay? This is, by the way, this is all I put into the website today morning. So 2 NO2 molecules will collide to make N2O4. However, this reaction isn't very spontaneous. In fact, it easily achieves equilibrium. Okay? Equilibrium is a scenario where the forward reaction goes as fast as the reverse. So as much as 2 NO2s collide to make this molecule decomposes. Okay? And a great way to look at that, all right, is to take this. So what we did is we took 100%, like at times 0, I have 0 N2O4. That's my product. I have 100% NO2. As time proceeds, what happens? Well, I'm going to make some of my products, and I'm going to use up some of my reactants. Where is equilibrium established? When they stay constant. What is equilibrium? As a review, it's not when these chemicals are equal. They will never be equal. It is when they stay constant. Why? As fast as I make N2O4 is as fast as the N2O4 decomposes. So if you think of it this way, I have 10 people on this line, 2 people on this line. I ask people to switch lines every minute, 1 person per minute. The people will change, but the actual number will be what? The same. So one of the key understandings of equilibrium is that the concentrations are not changing. Where is this process spontaneous and where is there no spontaneity? What part of the graph do we have a pathway? What's that? Perfect. Absolutely. You have a clear pathway. Things are changing. It's going from, but then, when we reach equilibrium, is there any net change going on? No, there's no pathway. So we went from spontaneous to none. So when we're at equilibrium, battery dies. There's no spontaneity. And if you look at this carefully, even though rate is not measured with spontaneity, I know people are having a hard time with that, but I'm trying to help with that, and we'll see more of that. We're very spontaneous here, no spontaneity. Equilibrium, that position. Now, it just so happens that this reaction easily attains equilibrium. What do you think that means? That the forward rate wasn't all that what? Spontaneous, correct? If you can have a reversible reaction compete with the forward, that means one of the directions isn't all that spontaneous, correct? Yes. When I combusted things this week, burned them, is the ability for the CO2 and water to combine back into, let's say, ethanol or the cotton ever going to happen? There's no possibility. That is so spontaneous, equilibrium is never achieved. So not all reactions can reach equilibrium. Only the ones that are low enough on the spontaneity line. Okay? So what does equilibrium look like? My gosh, guys, it's about as sexy as I am. Not. Okay? It's boring. This is a tube of NO2 and N2O4. By the way, NO2 has a brownish red gas. N2O4 is clear. Is it getting darker? It's getting lighter? No. Under the set of conditions that I'm at, certain temperature. It's an ampule, by the way. By the way, this is a clear tube with a brown gas in it. Both gases. Don't think it's a colored tube. I've got to explain. This is called an ampule, a clear glass tube that has a brownish gas in it. And both gases are existing in equilibrium. The color is not changing, so it tells me that we're in equilibrium. It's also telling me who's favored. The brown color, which is the NO2. Now I'm going to change the conditions. I'm going to put some in ice, put some in high temperatures. I'm changing the conditions. Don't forget, E0 cell is based on what? Conditions, right? Okay. Now let's continue on our discussion. Now, because we're at equilibrium, does that mean that there still isn't a favored way to go? Like, isn't it favored? Even though I'm at equilibrium, is there still more NO2? So even at equilibrium, we're not equal in amounts. There's still a favored way. Okay? NO2 likes to exist. Now, why do you think? Think with me. Why do you think, even at equilibrium, the favored direction, and you guys learned this as KAQ last year, we'll get into it later in the year, is still more reactants than products at equilibrium? Think with me. Two things make one. Where will I have a more dispersed product? The decomposition or the what? The synthesis. Synthesis, for those that are getting lost, where am I going to have a favoring? Think about it. The synthesis or the decomposition? Where does it want to exist? Doesn't it want to exist as free particles? I am locked up as 2 nitrogens. Hey, I'm moving and moving, and all of a sudden, boom, I can be a free nitrogen, and my own NO2s are flying around different from that end. Where is there more dispersion of energy? So, doesn't it make sense at equilibrium? It's going to probably exist in this form. That's why there's more what? NO2. What does spontaneity mean? Don't forget, dispersion of energy. It follows the flow of nature where we're following a pathway where we disperse energy from what? High concentrations to low. That has to be understood. Now let's continue. We measure whether something is spontaneous by the second law of thermodynamics. And we'll get into this more details, but I want you to understand delta S is the entropy. It's the change of the dispersion of energy. We want the dispersion change to increase. So we want the change in the universe's overall to increase. And you guys learn it as disorder. It just so happens particles that are smaller and freer have more motion than particles that are what? Locked up. You learned last year entropy is the measure of disorder. That's the Regents' definition. Entropy is what? Tells me something about dispersion of energy, which tells me what? Something about the pathway, whether a reaction will go forward. Do you see now how this means a heck of a lot more than just seeing if one thing breaks into two? Do you see that? That's what this course is about. Now, if the energy is not dispersing into the universe, then there's no pathway for the reaction. It's not spontaneous. If the reaction is dispersing energy into, it does work. That is how the universe works. See, we think that we can do anything. We can make an engine that's totally what? 100% efficient. Can't do it. Why? Why can't I take an engine and figure out to make it 100% efficient? Every time you have an engine, it gets hot. You can't use all of the fuel in the engine to move the car. You have to lose some as heat. Because if you didn't, party people, it wouldn't work. Why do we have to give off heat? To make the universe more what? Disperse the energy. You can't do it all. You're locked by those rules. You can't make cold flow to hot. Did I give you that scenario? Why can't cold flow to hot? You guys know from rule, hot flows from hot to cold. Why? Think of particles. Why? What's that? Right, good. You see, you're understanding. Think of my friends, of people that I know, okay, sitting in Central Park measuring blades of grass. I like to take, I know people who do this. Okay, we take 10 blades of they take 10 blades of grass. We measure how fast they grow. They do. It's so fun. They tell me it's fun. Okay? And you spend a whole day measuring blades of grass. You have 10 of them. You have to be there very slow because wind could change the blade of grass. And there's 10 of us sitting in 10 of them sitting in a 1 square meter. We're moving slow. Okay? It's really, they tell me it's interesting. Okay. People always run into them while they're doing this. Okay? Why? Because we're moving slower. If you're moving slower, you don't get to the fast the fast particles come to you. It's that simple. Okay? But it's really what? That law. Hot goes from high to low or hot to cold because we're dispersing energy. By the way, when all the energy has been dispersed evenly, what do you think you have? Death of the universe. When all the energy in the universe has been spread out evenly, there's no more chemical reactions, there's nothing. There's no more pathway. Death of the universe. Don't worry, that's not going to happen until a couple of years from now. But can we have death of chemical reactions? When is all the energy dispersed in a chemical reaction? At what? Excellent. You have learned something today. It takes college people 3 or 4 years to understand. At equilibrium, at the point where the forward reaction equals the reverse, you achieve the death of the reaction because there's no more what? No more pathway because there's no more net change. If you're going as fast in the forward as the reverse and the amount of reactants and products are staying constant, there's no net pathway, which means there's no more what? Energy to disperse. You've reached the point where you've exhausted all of your stored energy, or there's no net change. Death of a reaction. Okay, that's what equilibrium is. Now the best way to explain it, okay, love it. All right, this is my diagram. I gave it to a textbook company about 10 years ago. Because I'm not a PhD, they didn't accept it. But somehow I got in there. All right? Fine. But in any case, I didn't finish writing. But here's the diagram I love. Now, my diagram's got some issues. I'm assuming equilibrium is 50%. Now what does this mean? 100% of my reactant, 100% of my product. I put equilibrium here for simplicity. Equilibrium is never 50% of both. Who's favored? Who's favored? The NO2. So really, my drawing should be like something like this. But I just didn't want to confuse you there, okay? Now, if I have 100% NO2, and reactions do what? They have pathways, right? But they have pathways toward their death. They have pathways toward they move toward what? Right! You have a lot of energy to disperse, and as you move forward in the reaction, you eventually get to what? And nothing happens. We all move to this position. So at point A, very spontaneous, which means what? The reverse is almost what? Zero spontaneity, correct? At point B, now I'm just saying, 60% NO2 and 40% N2O4. What does that mean? Am I as spontaneous? No, because I'm closer to having no more energy dispersed. I disperse that much energy in the reaction, that pathway. So as reactions go,
at this time, would all seniors please report to the auditorium?
At this time, okay, at B, there's a far less amount of dispersed energy. My spontaneity has what? Why is mine dropping? It's moving toward what? Right. Pathway's getting lower. Just in redox reactions, we can measure it with voltage. Other reactions we really can't. Okay, now, what is point C? What if I take 100% of the clear gas? Is the reverse reaction possible? If I have 100% N2O4? Well, no, because there's no what? NO2 to come back. There's no competition. So at this point, I'm very spontaneous in the reverse, which means the forward is right. What did we learn? If zinc is terrible at reducing, right? If I look up zinc plus 2 gaining 2 electrons, when you look at the reduction potential, what charge do you have? Negative 0.76. Why is it listed that way? It's listed as a reduction by convention. Why did I flip the sign? Okay, but you know better. If it's terrible at reducing, if it's terrible at going one way, it's better at what? Right. There it is. Question about this graph. So, what I want you to understand is these are shifts of equilibrium going one way. What's a shift at equilibrium really? It means that you're getting more spontaneous in one pathway. Something called the Chatelain's principle. I'm going to get to the lab real fast. The Chatelain's principle states, if you have a reaction that can be reversible, not all reactions are. Combustion is not, for reasons we explained. If you apply a stress to this reaction that's at or about, or can be at equilibrium, can achieve that point, there's going to be a response. Okay. We just talked about Don saying we're running out of copper plus 2. Let's say I physically take copper plus 2 out. Okay? And I can only change those that have concentrations. I can't change the amount of a solid. There's just a solid. You can only change the concentrations. Think with me. I have less of a solid. Does that change the overall entropy? If I have more or less free ions, does that mess around with the entropy of the universe? You bet your donkey. Free ions or not, that's an entropy thing. Okay? Now, so if I lower the copper plus 2, we physically lower the copper plus 2. It's right here. We have less than we should. Okay? Think with me, party people. Watch. Here's my U. Here's the death equilibrium. Here's 100% what? Copper plus 2. Here's 100% what? Zinc plus 2. Here's my products. Product, reactant. You with me? Now, by lowering copper plus 2, I was at this position and now I'm going where? I'm lowering the amount of copper plus 2 that I should. I'm going where? Yes, this is moving downward. If I'm moving downward, I'm becoming more spontaneous or less? Right. Okay? So I'm moving downward. the response by the reaction, okay, is to increase copper plus 2. All right? Now, the real reason is, with Le Chatelier's principle, they like to say when the reaction is at equilibrium. So let's pretend we have a dead battery. So I'm right here. It's not spontaneous, correct? Now, let's say I lower copper plus 2. So now I go where? I move it upward. Here, correct? Where does reactions always move? Toward lower energy dispersed. I have a lot of energy. The pathways always move toward equilibrium, toward the cell what? So if I have less copper plus 2, this would go this way. Okay? And therefore it's going to want to do what? Increase backward. That's Le Chatelier's principle, guys. You learned it last year. If you decrease something, the reaction is going to do the opposite to regain its balance. A little more than that. Okay? So the idea here is that if I lower copper plus 2, okay, and I think I got this backwards. My own little thing I messed up. Sorry, let me try this again. Okay? I have a reaction at equilibrium. I'm at this point. This is 100%. I can do this. Okay, at this position. It's 100% zinc. Now, if I lower copper plus 2, I went the wrong way, my bad. Sorry. If I lower copper plus 2, shouldn't the copper plus 2 go here? Yeah, I'm sorry. Okay? And if you saw that right away, speak up. I make mistakes, I'm told. Okay? I'm sorry. That make more sense, right? That's 100% copper plus 2, and this is less of it, right? Because eventually I get to what? 0% copper plus 2 and 100% zinc plus 2, correct? So my friends in chemistry, what's happening here? If I'm at equilibrium and I move this way, what's now going to happen? It's going to be spontaneous this way. The reverse reaction happens. What does that mean? Last year you learned to be the what? It shifted to the left. Beyonce. What does it really mean? The reverse reaction is now more spontaneous. Okay? If I do what? Decrease zinc plus 2. So if I have my equilibrium, pretend, and I decrease zinc plus 2, this would be having more zinc plus 2. This would be what? Less zinc plus 2, correct? Where would the reaction move toward? It's death. It's going to move spontaneously where? To the right. Now we have easy rules. It's Le Chatelier's principle. You lower zinc plus 2. If I was teaching Regents chemistry, I would say the reaction shifts to make more zinc plus 2. It wants to regain its balance. If you have too much copper plus 2, the reaction is going to shift to lower it. What if you have too much copper plus 2? If I add more copper plus 2 here, the response by the reaction to regain its balance, if you want to use that, is what? To do the opposite, right? Copper plus 2 does what? Goes down. How does it go down? It goes down by using it up. Right? But if I increase copper plus 2, I'm starting here. Aren't I moving up? And now it's going to be what? If I move out of the equilibrium position either way, it's going to go the opposite to go back. Why? What's that? It wants to move toward the death of the reaction because that's the way that you what? Disperse the energy. Okay? All right. Take out your lamp.